we got ourselves a graph, and I want to add some information into this graph. First thing, let's turn the page sideways. First thing, let's give some axes labels. We're going to make this be the position axis. I want to offset my label enough so that I can add in some numbers after. So we're going to make this the position axis in units of meters. And really, if this was a formal graph, we would use the full word position and we would capitalize it. I'm just using symbols. And we're going to make, just for argument's sake, let's make north be positive. Now, when we do add in these numbers, we're going to add them every 2 squares, like this. Okay, so I'm going to rotate that back again. And that vertical axis is going to be, at those points, 10, 20, 30, and 40. Now the horizontal axis, we're going to let it be time in seconds. You know, we can have a continuation arrow on the ends here. I know that I have some math teacher friends that feel very firmly that those arrows have to be there, and that's fine. They can be there. But then along this axis, we're going to call this, or we're going to have a scaling so that every 3 squares, we're going to go up by 50. So 50.0, 100.0, 150.0, 200.0, and 250.0. Okay. And I'm not going to dress this up with a scenario. I'm not going to say, oh, we ran down the street or the hallway. Let's just take it as raw data, kind of like in math class. Let's just not give it a context. Let's just say we're going to analyze this and talk about how to analyze it. So what I would say is I've got myself 2 positions that I want to define on the page here. At this point right here, and at the 200-second mark and 40-meter position, another point. We've already talked in the past about what the importance is for position time graphs in terms of calculations, but we'll get back to that again. I want to just for now draw a line of best fit between those two and say, look, someone did some motion, and the motion they did looked like this. Let's analyze this thing. Well, if we were going to analyze this, we'd say, all right, well, there would be a rise, and I'm going to use proper variables. So that rise wouldn't be delta y, it would be delta d. It would be the change in position. And you notice that we really are, we're dancing around different languages. The language of English, the language of math, the language of graphs. We're dancing around different, even the language of diagrams. Dancing around different languages in physics, and the analysis of physics in that respect very much is multimedia. So over the course of that motion, we also have time that's gone by. So I got my line of best fit, and I've sketched in a rate triangle as big as I could to talk about this line of best fit. Now, what we've done in the past with these kinds of rate triangles is we've found rise and we've found run. And in this specific context, rise over run is displacement over delta t. And what we've claimed already is that the name we give to that displacement over time is called the average velocity. Average velocity, and that average velocity has a direction. What we know from the way rise over run works is that this V average, I'll short form it as VAVG, V average could be written as D2 minus D1 over T2 minus T1. And we could sub in values. We could say, okay, well, D2 was, anyway, shout it out, what's D2? 40, yeah, look. This is the second position. We always read from left to right. This is the first position. So D2 is going to be 40. D1 is going to be 10, yeah. T2 is 200, yeah. T1 is 0, yeah. So somebody who's quick on the draw with a calculator, what's 40 minus 10 divided by 200? Yeah, so 30 divided by 200, what is it? It's a nice round value. 30 divided by 200. 0.15, nice. 0.15 meters per second. And the fact that it's positive tells me what direction is it, based on the axes that we drew. North. You look, that north there in the vertical axis, that defined north as the positive direction, okay? So that's something that we've declared, even though we didn't have like a cruciform, like a cross-shaped north, south, east, west direction, we declared north to be positive on that graph axis. So now we got this positive velocity north. All right, that's great. But I feel like we've kind of been there before. So sometimes we think this way. Sometimes we think this way. And what I'd like to do is take this position time graph, and I'd like to do what people sometimes call translating it. I'd like to translate this graph into a velocity versus time graph. And I know this isn't a formal graph, but if it was formal and if this was considered to be the title, it should be below. It's not the title, it's just sort of like the heading for the section, okay? So don't think that we messed this up or something in that way. One thing though, when you're translating graphs, a popular thing to do is to stack translated graphs on top of each other. The reason is if you stack the translated graphs on top of each other, it's totally rational. Look, this 50 gets mapped down here as a 50. Basically, we line up the time axes, which means that the story being told on one graph and the story being told on the other graph are kind of in sync with one another, and we can see how they relate to one another. And so you'll see this when we're doing this right now, but you'll also see it in software. We might even use a probeware tool called LabQuest. But when you have multiple graphs that are just different aspects of the same motion, like position, velocity, acceleration, but for the same object, all being mapped simultaneously, it's really common to have those graphs stacked one above the other because the time axes would just sort of be synced with one another, and you can see it kind of happening. And I think that anyone who's done any audio-video editing, you know when you do audio-video editing, it's like you can see stacked tracks of audio and video that are like synced up with one another. Like maybe you have the music track, the dubbed over vocal track, and then you have the actual video track on top of each other. It makes total sense that you would want to sync up the timelines like this. This isn't obviously the same thing, but we're looking at different aspects of the same presentation, which could be in this case position information and velocity information. Now, it's a decent sales pitch, right? All right, so I got my time axis. That's my horizontal axis, and yeah, if you really like those arrows, we can add the arrows in. And if we go to the vertical axis, in this axis, instead of position, we're going to talk velocity. So V. Oh, and I didn't give myself enough space. You be better than me, okay? I'm gonna white this out, give myself a little bit more space for the labeling of the numbers. Velocity in meters per second. See, this is why the chemistry folks like to have pencils. Velocity in meters per second. We're still preserving north as the positive direction, so that doesn't change. It's the same reference frame. And then I say, okay, I think for this one, I'm going to set a scale every 2 squares, but I want you guys to have some insights as to why I'm setting this scale. It looks like, wasn't the average velocity 0.15 meters per second? And wasn't it that velocity the entire time? Because the slope was the same the entire time. And so when I come down here, this is a very basic translation, but when I come down here, what would be true about the velocity the entire time? I heard the word constant, it would be 0.15. And so if it's going to be constant or 0.15, What shape of graph is this going to be? It starts with an H. Horizontal, just a straight up horizontal graph, right? So hey, I think if I'm going to only have 0.15 the whole time, my scaling, it makes sense to have this be 0.05, 0.10, 0.15, 0.20, because my math teacher once told me that I should try to make my graphs kind of fill the space. I don't really want my graph to like hit the ceiling, but I want it to sort of hit the space, or fill the space. And so my data goes from 0 seconds all the way up to 200 seconds. Now, I overshot just a little bit here. And so I'm going to do a little bit of whiting out, because my data doesn't actually go beyond 200 seconds. People say, well, what do you do if the data doesn't go beyond a certain point? That's okay. The data instantaneously stopped, and so we're going to have a vertical dotted line that indicates instantaneous stops or instantaneous changes in motion. Okay, so that vertical dotted line holds a meaning. It just means everything stopped right there. I'm not going to pretend that it kept on going, because I don't know what happened. So we have some rationale for why we scaled it. We've got some notation for how we stop things. Now I want to take a look at this graph. If the graph above was something that interested me for its slope, this one, I actually could look at the slope. Maybe I'll come back to that in a minute. But something else that people talk about for graphs is area. And that's something we have not talked about in math class. It's not something that shows up in grade 9 or grade 10 to find the area under a graph. There are people, I know because my own kids will go watch these YouTube videos and they'll say, oh, Daddy, the area under a graph, that's calculus. You guys ever heard that before? You ever watch one of these, like, I don't know, a TED Ed video or something like that? How many, put your hand in the air if you ever heard of this before. Area under a graph, that's something to do with calculus. Turns out the slope of a graph is connected to calculus too. But let's talk about, in this context, what the area means. So the area here, well, we all know that the area's got a formula. Area of a shape bound by a graph the area for this shape, which is a rectangle, is equal to length times W. And if you're not sure what rectangle I'm talking about, let's just like really make it pop with a highlighter. We're talking about finding like this area, okay, this rectangle. That's the area that we're trying to find, length times width. Now, we wouldn't call it length times width, we would use appropriate variables, but let's just come back to that in a second. Let's talk about units first. If I take this length and this width, can we agree that the units would be units of seconds times a width, I know we might think of it as a height, times a width of meters per second. And if we just looked at the units, this dimensional analysis, notice the seconds would cancel out, and that would make the units into meters. And as soon as I do that, I'm like, oh, well, the area of a velocity time graph must have a meaning, and based on the units, what do you suppose the meaning of a velocity time graph's area is? Starts with a D, rhymes with displacement. It is! You're right! It's displacement, right? Like, it's displacement. So, let's talk about how that's the case. Turns out that if we go back to the equation, V average is equal to delta D over delta T, and I rearrange this thing to get V average times delta T equals delta D. As soon as I do that, you see that delta D equals, I could rearrange it if you wanted to, delta T, that's the length, times V average, that's what we call the width. This formula and this formula are actually just the same formula dressed up differently. And so for that reason, we can make this claim. We can make the claim that the area under a VT graph, that is a velocity time graph, that's short form, is displacement. And there's always going to be people who say like, well, that's a rectangle. What if it's a weird shape? Trust me, it's still going to be true. And we can investigate weird shapes later, but for now, I just want to make this claim, okay? So this is a rule. The area under a velocity time graph is displacement, and then the slope rule that we talked about last day was that the slope of a position time graph is velocity. And so there's different things we can calculate from these different translations of the same motion. And which one you do depends on which graph you're working with. Now, if I wanted to reflect on this and say, hey, I'd like to find the displacement from graph, the first graph, I'll call it graph I, the one at the very top left-hand corner of the page. I could say, oh, that's easy. The displacement based on that graph, delta D, the displacement, is D2 minus D1. That was actually what we called the rise for that graph, and it was just positive 40 meters, where positive is north, minus positive 10 meters, where positive was north, and we get 30 meters. On the other hand, if I was going to find the displacement from graph I, that's the one that I just shaded in pink here. Yeah, I. Then we use that formula, delta D is equal to V average times delta T, sub in our values. Well, V average was 0.15 meters per second, and it happened to be positive as well, which means north, times delta T, 200 seconds. And nobody at all is shocked to know that that's equal to 30 meters. And it's positive, so it's north, both of them north. We say, well, fantastic. This is what they call an internally consistent argument. We've got a bunch of stuff that all kind of fits together, in other words. And that's what you want. You want all the rules to fit together. I know people want to have that for a second more. Can you guys give me a wave to let me know that it's all good to go? How many? Oh, thank you. I like that royal wave. Beautiful. Anybody need a minute more? All right. Got the thumbs up. Keep on going. Don't worry if you really do fall behind, because I know there's always people that have very slow handwriting. You can always come back to me afterwards, because we won't wait forever. We got to keep on going. If you have very slow handwriting, you can come up to me and say, hey, can I get a picture of this or that from the notes? I'll let you take a picture. It's not a big deal, okay? Or you can get it offline, off the internet. All right, so the rules, just to put them kind of all into one place. We've got the slope of a DT graph is velocity. We say V average is equal to delta D over delta T. The area under a VT graph is displacement. And it might get more complicated than this, but our first evidence is that displacement is equal to V average times delta T. There's a third one. And the reason it hasn't come up is because I haven't asked you to analyze this kind of graph yet. But it stands to reason that there must be something we could do with the slope of a velocity time graph. Because, I mean, sometimes a velocity time graph might be slanty, you know? The slope of a velocity time graph, I'm going to throw this out as a fact, and we'll take a look at the implications, like when we actually analyze a graph in a second. But the slope of a VT graph, anybody want to guess? Yeah? Acceleration, yeah. If the rate of change of displacement or position is velocity, then the rate of change of velocity is acceleration. So we say acceleration is equal to the change in the velocity on a slanted velocity time graph divided by time. Hey, just a couple of points of trivia before we go on. A little bit of a note off to the side in the margin. When I talk about delta V, I will always mean V2 minus V1. Okay, so anytime you see an equation that has delta V in it, there's a hidden binomial, V2 minus V1. Okay? The reason I say that is sometimes some people ask me, oh, what's the delta V variable? Like, where do you find delta V in the givens in a word problem or whatever? Well, you'll probably be told what its initial velocity and its final velocity were. You won't be told necessarily what the delta V is. You got to figure that out. Okay, so that's one thing. The other thing is V average. Sometimes you're told V average, but sometimes you're told the initial velocity and the final velocity. And so, again, reading between the lines, I want to make sure that people have this one. V average could be thought of as V1 plus V2 divided by 2. And that's especially going to be handy in one-dimensional problems, okay? So if you have a V average that you're trying to use, and you only know the first velocity and the last velocity, this is just a little trivia bit. Both of these guys are ones that you might not realize that information's buried. You know, you'd have to think about it a little bit. I mean, this one's just a straight up binomial. This is a binomial divided by 2. That's stuff you need to have to like write down all your givens and keep track of. Yeah. Oh yeah, I'm going to give you a formula sheet for every test. Okay, right, and the exam. In fact, I'll staple a copy to the back of your exam so everybody's equal and you all have the same information sheet. So somebody's not better at making a cheat sheet than another person or something like that. Okay, but yeah, you all are going to be treated nicely. We want to be a problem-solving group. We don't want to be a memorizer of all kinds of facts. Although I would argue that if you're doing all your homework, you're going to have these equations memorized anyway. And you look at that equation sheet and you think, no, not me. Yes, you, if you do your homework. And it's impressive what you can memorize if you're using a toolbox over and over again, you know? Anyway, I want to take a look at this graph. This graph says it's going to be a velocity versus time graph. It's getting a little bit more formal. It's got the units at least. It doesn't have a title underneath. Remember, it is just a heading, so don't get too critical. But I do want to turn it sideways just like we've done already, and I want to give that vertical axis a label. So I want to call the vertical axis a velocity axis. I want to make it meters per second. I want to make, this time, just to be different, we'll mix it up. Let's let east be positive. And in terms of the scaling, I'm going to keep it really simple. I won't even put any decimal places on there. In terms of the scaling for the vertical axis, we're just going to go 1, 2, 3, 4, 5, 6, and we'll go up by ones. 1, 2, 3, 4, 5, 6. So nothing fancy. Now on the horizontal axis, we are going to label it as time. Oh, this one's got arrows. That's nice. And every other square. Every other square we're going to make go up by 1 second. Again, keeping it nice and simple. Up to the 7-second mark. And then I want to add in some data. So it looks like, I think at the 2-second mark, let's say that we get up to 5 meters per second. And then by the 4-second mark, we get up to 5 meters per second still. And then around the 6-second mark, let's say that we're going at, oh, you know what? I didn't go down. Oh, gosh. 1, 2, 3, 4, 5. Let's go all the way down to 5. So -1, -2, -3, -4, -5. Going down that axis. Oh, good catch, Killens. All right. So down to 6. We're going to go down to, I think I had it marked off as -5. Okay. Now we're going to do a little bit of connect the dots. Because I know that with position time graphs, I said, oh no, you're always going to do lines of best fit. With these velocity time graphs, sometimes we're going to analyze graphs where the velocity instantaneously changes. You know, like the speed changes on a dime. And I know and you know that in reality, if you're in a car and you want to instantly go from 0 to 60, that is not a possibility, is it? You can't just go from 0 kilometers per hour to 60 kilometers per hour, boom, in a snap. In fact, that's one of those things for performance ratings. They talk about how fast you can accelerate to, 60 or 80 or whatever it is, right? So we're going to add this simplification, which is to say, in physics world, in grade 11, we can instantaneously change our speeds. That can be a thing, okay? Or we can instantaneously accelerate. That sometimes is a thing. And so what's going to happen here on a graph is that when we graph these things, we can go, gradually from 0 meters per second up to 5 meters per second. But we're going to be able to instantaneously maintain that 5 meters per second. I know that with cruise control, it would kind of like phase in and out just a little bit, okay? So those of you, the reason I'm sort of drawing attention to this is those of you that are into autos are going to know this. Not everybody realizes, you don't instantaneously switch over to a constant velocity. So we're going to have these weird geometric shaped velocity time graphs, even though in reality they'd be curved on the corners, okay? Makes it for us easier to analyze, and it also requires that we don't have to know calculus yet. That's really what it comes down to. Now, if you're somebody who has done some of the math classes where we're talking about functional notation, f of x's, the fact that this isn't a curvy one, no curved corners, means that this wouldn't be a great candidate for making an f of x equation. You guys know what I'm talking about with this? It would be a weird shape anyway for an f of x. That doesn't mean that we couldn't take all the data points along here and put it into a graphing calculator like Desmos and produce an f of x equation. If we did that, we could do some really wonderful calculus on this thing. But we're going to steer clear. So something that I want to draw your attention to, especially if you're somebody that's doing a calculus course or you're reaching ahead or whatever, because this is grade 11, is that, there's a bunch of stuff that we'll be doing that we're going to just skim the edge of calculus on. We're going to stop short of doing the calculus-y way of doing things because I can't expect that everybody has that under their belt. And once you do have calculus under your belt, think first year university, you better believe everything is going to have calculus embedded in it. Everything's going to have linear algebra embedded in it. So we're just dancing around the edges of calculus, obviously with complementary material, but it's going to be a temptation for those of you that are reaching ahead. We just can't reach ahead, okay? Because we're going to assume that nobody has ever heard of calculus before. Cool? All right. Now, as I look at this, I think, wait a minute. Velocities, areas, slopes, that's a bunch of that stuff that's rule number 2 and 3 up above. I'm looking at this. I think I might want to break up a trip like this into portions. And sometimes people will call these legs of a journey. So this first bit, this second bit, I've got a third bit here, and then actually I'm going to be careful. I'm going to draw my triangle like this. Look how my fourth bit, see how I drew the triangle? I'm going to ask you to do the same thing because I could shade these areas in. I could say, hey, look, I got this triangle of space here. I've got this square of space here. I've got this triangle of space. I've got this triangle of space. And what I've just done is I've colored in all the spaces that are between the plotted data and the axis. This is the data that's between, or the space that's between the plotted data and the axis. And I would even say I've got area A, or region A, I've got region B, I've got region C, and I've got region D. And if I was somebody who's talking in maybe an old-timey way, there would be 4 legs to this journey. There would be leg A, leg B, C, and D. 4 distinct portions to this journey. And I want to be able to talk about what's happening in these 4 distinct portions. So in A, what's happening to the speed? I heard somebody say accelerating. Is it speeding up or slowing down? Speeding up, okay. So let's say it both ways, speeding up. Accelerating to the east, based on our direction that's on the vertical axis there. Speeding up, accelerating to the east. I'm trying to put some words on this graph because really graphs are a way of telling a story. And so we should be able to, again, translate back into English to tell the story, the narrative of what's going on here, right? Like, I don't know what this is. Maybe it's a car. This car is accelerating as it travels east. What's happening for portion B? Somebody else. It can't be the same person every time. Yeah. Staying the same what? Same speed. Yeah, it's going to stay the same speed. So we could say it goes east at a constant, actually I can even say constant velocity, right? Because we've got direction here. At a constant velocity. Oh, you know what? This idea of constant. If I have a velocity that stays the same, I usually say that it's constant. This portion A, is the slope the same the whole time? If the slope is the same the whole time, the acceleration was the same the whole time, right? Now, in terms of buzzwords, people don't usually say constant acceleration, although sometimes I slip up. What we're really sort of coached towards saying is uniform acceleration. And that's a way to distinguish between what we're talking about with velocity and acceleration. So this one here, I could say it's speeding up. It's accelerating east. I'll say uniformly. Okay, so that uniform acceleration means that it's accelerating with the same slope on that velocity time graph. Anyway, portion C. What's happening at portion C? Yeah? Okay, we could say decelerating, and then that's going to be something that a lot of people say because, I mean, that's the language that we would like to use, and you'll even see it in textbooks and online. I'm going to try and force this idea of accelerating negatively. So we're going to have negative acceleration. Not only that, is the slope constant or does it change? It's constant, so uniform negative acceleration. So let's try to throw all the buzzwords out there, you know? Uniform negative acceleration. And actually, the math folks are great with talking about this with functions, about critical points. There's a critical point that's going to happen as it crosses the axis. It's critical because something noteworthy happens. What happens to this car if it was a car and it passed the axis? Yeah. It's got zero velocity. Look at this. Like right here, if we're reading this, every time I move my pen along this graph, I'm looking at the vertical axis to see what's happening. Speed goes up, speed goes up, speed goes up. Speed stays same, speed stays same, speed goes down, speed goes down. And then at this point here, she's right, zero velocity, and then the common people among us would call that stopped, right? So it's uniform negative acceleration coming to a stop. And you know what? Instead of saying coming to a stop, I'm going to use one of the other common words that people use, coming to rest. But does it stay at rest for a long time? So I'm just going to say it comes to a rest for an instant, because it's not actually going to stop there for any duration of time. Instantaneous stop. And then portion D, I think I'm running out of space, so I think I'm going to loop the loop and come over here. Portion D, what happens to this thing? Yeah? Yeah, it does. It starts to reverse, traveling west. So we've got a direction associated with it. What about its motion? Is it speeding up, slowing down? What's going on? It's accelerating. And actually, here the thing is, when I lay my ruler down here, you notice that for portion C, we're saying that it has negative acceleration. Now, you got negative acceleration and you're traveling to the east. That's going to slow you down. But if you've got negative acceleration, a negative slope, and you're traveling to the west, what's that going to do for you? Speed you up, yeah. So I'm going to make a note of that. We say it travels west with negative acceleration. and speeds up. Because remember, speed is independent of direction, but it's getting faster. And when I take a look at my graph, I think, well, what does that mean to speed up? You notice that anytime I get further from the time axis or larger in magnitude, that's a fastness, right? That's an increase in fastness. In this case, I'm getting further and further away from that time axis. I'm getting faster. It just happens to be fast in the negative direction, right? So we want to be able to make sense of what it means to read over to that vertical axis. It's getting faster and faster as you get further and further from the axis. Happens that sometimes you're faster in the positive direction, sometimes you're faster in the negative direction. And as I look at this, I think, hey, if my acceleration, my slope of a VT graph is negative, but I'm traveling in the positive direction, it'll slow me down. If my acceleration is negative and I'm traveling in the negative direction, it's going to speed me up. That seems like some sort of abstract stuff there, but it's stuff we have to keep track of. There's a lot of things that are sort of going on here. Now, what I want you folks to do in terms of math, could you take a minute, and we've already shaded these in, could you folks please try to find delta dA, delta dB, delta dC, and delta dd. Let's figure out how far and in what direction they went for those shaded areas. Okay, and I think from a video recording point of view, I'm going to pause here. I'm going to give you guys some time to work.